Okay, so first we'll try to understand what is the experiment, what we are trying to do. Then we'll simulate that one and observe the performance. Okay. So what is the experiment? Yes. What is the experiment?
Understand the cost, slow start, congestion avoidance.
Any idea what it is saying? We have studied in theory class, right? Congestion control in TCP. So anything you remember is from that? We'll start with. Okay.
Initially, it will send one packet. After getting sent automatically, it will double the. It will send one.
In slow start phase, you are going to do that. Then next one, congestion control, multiplicative, congestion avoidance, and multiplicative decrease. Three phases are there. Okay, so we'll try to understand what is done in TCP. So basically in TCP congestion, we have various types. Okay. The types which we are going to discuss are old Tahova. Then we will consider Tahova, TCP, Reno. Okay, these are the three things we will be considering. So whatever the mechanism we have studied in class or in theory, that is related to old Tahova. So what happens in this one is, we are going to have three phases in TCP congestion control. One is slow start, then congestion avoidance, and the last one is multiplicative decrease. So these are the three phases we have. So basically what happens in slow start is, we will consider one maximum segment size. Okay. We will write that one as 1 MSS. Basically, whenever we want to send, we need to decide on what is the size of packet we need to send, right? So here we will be considering congestion window size equals to 1 maximum segment size. Window size basically it is dependent on receiver window size and congestion window size. So congestion window size we are going to consider 1 maximum segment size. What is 1 maximum segment size is? What is the maximum size we can transmit on a particular channel? That is considered to be maximum segment size. Okay. So 1 maximum segment size we are going to consider in slow start, and what happens after that one is, let us say we have considered 1 maximum segment size. I'll transmit that one. I get acknowledgement for that one. Then next time I'm going to send second and third 2 MSS amount of data we will be sending. Okay. I'm not saying like 2 at a time we are going to send, like in single segment we are not going to send, but it may be 2 segments which we are sending, because the underlying channel it can carry only 1 maximum segment size, right? For example, if I consider internet, it will have capacity for 1500 bytes. Maximum it can take 1500 bytes. More than 1500 bytes you cannot send. So in that case, MSS size will be 1500 bytes. So 2 segments we will be sending. If I get acknowledgement for 2, I am going to consider 4. Okay, 4 number of segments I mean. So 4, 5, 6, 7, all those 4 will be sending. Then if I get acknowledgement 8, 16, then 32, 64, like that will be increasing. So till when we are going to follow slow start? Any idea? Yes. Till when we are going to follow slow start? Till we reach something called as SS threshold. What does it mean is slow start threshold. Okay, we are going to have some value for slow start threshold. Let us say the threshold value we are considering is 64. Okay, at some point of time we will reach 64, right? After reaching that particular point, we are going to move to additive increase state. Okay, from slow start, we are moving into additive increase. So I was in slow start. Whenever threshold reach, I am going to additive increase. In additive increase, what happens when you send 64 MSS or 64 segments you are sending, you are going to get acknowledgement for that. Next time I'll send 65. Okay, plus 1. That's it. We are going to add one more segment to this particular count and we will be sending. I get acknowledgement for 65. Next plus 1. Okay, earlier we were doubling. We started with 1, 2, 4 like that. But you can see exponentially it will be increased. Okay. And next additive increase means only one segment we are going to add whenever we get acknowledgement for that. That will be continued till we experience some congestion. How we will say like congestion happened? Congestion is happened. That congestion happening will be identified because of two cases here. One is RTO, that is retransmission time mode. What does it mean is, for example, you are sending some message, and if that is not delivered at the other side, you won't be getting acknowledgement. After some time, you are going to fix some timer value, right? Whenever it expires, you will be retransmitting that one. So whenever RTO timeout happens, you will consider like congestion happened. This is one case. The other case is you may be receiving 3 duplicate acknowledgements. Okay. When I will be getting 3 duplicate acknowledgements, it's like I have sent first and second. There is no problem. They have been delivered. Then I sent third one, but it was lost in the middle. 4, 5, 6. I sent and they have been delivered. Whenever second one was delivered, immediately other person will respond. I am expecting sequence number 3. Third one mixing. Whenever fourth one is received at the other side, going back to the rules of acknowledgement generation, the receiver has to send an acknowledgement telling what is the expected sequence number. I am getting 4, but that is not expected sequence number, right? I am supposed to get 3. So it will tell 3. Again I got 5. I am going to send again like I am expecting 3. I got 6th segment. Again I will send, I am expecting 3. So how many times at this side we have received, I am expecting 3, 1, 2, 3, 4. Out of which 3 duplicate acknowledgements are there. So as soon as you receive that one, you will be sending the third one. That is called fast retransfer. Okay. So we have the terminology fast retransfer. So RTO timeout, you are going to retransmit normally whenever timeout happens. Whenever you receive 3 duplicate acknowledgements, you are going to go with fast retransfer. So which one is a longer problem and which one is temporary issue? We have two issues. One is because of RTO. Packets are lost. Packets are lost because of which RTO timeout happened. And there was one missing packet because of which we got 3 duplicate acknowledgements. Which one you will consider like it will last for longer duration? Which one? RTO. Why? Why not 3 duplicate acknowledgements case? It means nobody has concentrated in class. Same question I asked in class also. And I explained the answer also. And I said that is important question. Right? So, for example, let us say the problem is temporary. What happens? Any one of the packet will be missing and remaining packets will be delivered. But if I consider the problem is for longer duration, even you won't be getting 4, 5, 6, right? They won't be delivered at the other side. If the congestion in the traffic is for longer duration, you won't be receiving 4, 5, 6, and I won't be getting 3 duplicate acknowledgements also, because they will also experience congestion, right? So if the problem is for longer duration, even I won't be receiving this 3 duplicate acknowledgements. So if the problem is temporary, then only I will be getting this one. If the problem is for longer duration, I won't be receiving anything. So I cannot handle these two things in the same manner. Earlier days, whenever we had whole Tahova, they thought like we can handle the case of RTO and the case of 3 duplicate acknowledgements in the same manner. But later they thought like, when the problem is for temporary, why we are starting with same procedure for both the cases, RTO and 3 duplicate acknowledgements? That was the question raised. Then they moved to Tahova. First they had old Tahova, then they have come up with Tahova. Then later there is a problem with Tahova also, then they are going with Reno. So we will try to see what happens in old Tahova first. In old Tahova, like we were going with the additive increase, right? Whenever RTO timeout or 3 duplicate condition, 3 duplicate acknowledgement comes, we will be falling back to 1 MSS. Okay? That means we are coming back to where we have started. And again we will go with slow start, like in the case of old Tahova, slow start, additive increase, multiplicative decrease. Whenever condition happens, again we are coming back to slow start. Okay. But as we discussed just some time back, there is no need for coming back to slow start whenever we had 3 duplicate acknowledgements, because that is a temporary issue. You cannot have such a strong rule wherein you are starting from the beginning again. Okay. So what they have done in Tahova is, instead of coming back to slow start, what they are doing is, for example, if the condition window size, if this is the condition window size, whenever we experience the condition, we are going to make it half. Okay, if the value is 100, at 100 bytes or 100 segments, whenever we send, we experience some condition. So what we are going to do is make it half. It will be 50, right? So instead of coming back to SS, we will consider SS threshold and condition window size as 50, and we will start with AI, additive increase. We are not going back to slow start. Okay. So what happens there? We are starting with 1 maximum segment, 2, 4, like that again. But here 50, 51, 52, like that we are going. We are not moving to slow start. Okay. So there will be some improvement with this one, right? Whenever we go here, okay, there will be some improvement. Okay. This we are going to follow whenever we have 3 duplicate acknowledgements. Okay. We are not considering this case for RTO time. RTO timeout, you will have to start with SS threshold, this one.
Closed.
But whenever we have 3 duplicate acknowledgements, instead of going back to slow start, we are going to additive increase. That is the variation. Okay. Next case we have is Reno, TCP Reno, where we are considering fast recovery. This one we said fast retransmission. Okay. Next case we are considering fast recovery. So instead of going back to this one, what they are doing is this condition window by 2 plus 3 times, they call it as SMSS, or what is the maximum segment size we have at that particular time. 3 times that one we are going to consider. Okay. So this one will be performing better than Tahova, because we are going to consider different window size here, right? A better window size we are considering in the case of Reno. That is called as fast recovery. So we will try to observe these 3 cases. What is happening in both Tahova, how graph is changing, and how it is varying in Tahova, and how it is varying in fast recovery. That is Reno. These things will be observed. Okay. So you can go to next thing. And sim new simulation, internet works. So we need the two routers and two white nodes. Done? Okay. So you can give connection from wide node 3 to router 1, router 1 to router 2, router 2 to second node. Done? So go to node 1 first node properties, transport layer, congestion control algorithm, old Takova. Congestion control, old Takova. Click OK. Now we have to configure link properties. So go to first link, that is between wide node 3 and router 1. Uplink and downlink speeds 20 Mbps. Okay. Second link, that is between two routers. So here uplink and downlink it should be 100 Mbps. Propagation that is also 100 microseconds. Okay. Then second router and second node same 20 Mbps. Then go to application. Three to four and packet size. Packet size 1460. Inter arrival time 400 microseconds. Packet size 1460. Inter arrival time 400 microseconds. So the reason we are selecting 400 microseconds is when we consider that the generation rate becomes 30 Mbps. Okay. Join here. Done. 4060 application data size and interarrival time 400 microseconds. And if you do the calculation, you will be getting 30 Mbps. So what is the capacity we have for link? Between node and router, what is the capacity we have? 20 Mbps. With what rate we are generating packets? 30 Mbps. So your generation rate is greater than capacity of the network, right? Then congestion should happen. Is it or not?
Yes.
Whenever your generation rate is greater than network capacity, congestion will happen. And we will try to observe whether congestion is happening or not. If it is happening, how this voltage above I is reacting to that. That we will be observing. Okay. Enable packet trace. And we'll have to observe Wireshark also. Once go to node 1, first node properties. Wireshark capture, make it enable. Online. Okay. Click OK. And the simulation time is 30 seconds. We don't need animation, you can directly select the other one. Okay, all of you go to Wireshark name. Wireshark window displayed in front of you. You can just see here. We are going to statistics in Wireshark window. Then TCP stream graphs. Then window scaling. Like this. Switch direction. Minimize this window. Training on See, we have some entries, right? Time entries. Any one entry you can select and then go to statistics. TCP once go to result window. Result window and see what is the throughput you are getting. Check that line. Command line. Press. Now go to websites. Pick direction. Generation select throughput, you should be getting 7.2. You got like that? Okay, and the graph also basically we are supposed to get some conditions, but it shows like in a time which means no condition happened.
ఇంతకు ముందు జీరోనే పెట్టా పెట్టి స్విచ్ డైరెక్ట్ వచ్చింది అదే మారిస్తే జీరో మారిస్తే ఎగ్జాంపుల్ ల్యాబ్ ఉండే
Select the string 0. Try to maximize this possibility. And once again, on the click switch direction. Switch direction. This should be great. See, all of you, we can see here, when we observe this graph, initially like we are falling to one maximum segment and slowly it is increasing, like how we discussed 1, 2, 4 like that. And at some point it is going to condition avoidance stage. There it is increasing additively, like +1, +1. Basically, this thing is in 10,000 units, right? So we are not able to observe one change. We are not able to observe. Then whenever congestion happens, it is falling down. Okay, completely it is coming back. So you can see in all cases it is coming back to one maximum segment size, right? We'll try to zoom it again. So you can see here we have almost doubling, like slow start, but here it is looking almost unique, like one step increase like that. Okay, it looks like almost constant because we are going with additive increase, wherein only +1 value will be added. Okay, so same way we will try to observe other condition controller values. Okay, so you can observe that, you can zoom and you can locate here and try to observe. Okay. Done? Done? Everyone? Done? Yes. Will we go for next one?
Yes, sir.
Okay, save the experiment and open it again. So next case again, you change congestion control algorithm, make it Takova. First node properties, make it congestion control algorithm Takova, and simulate for 30 seconds again. So in the case of Takova, you'll be getting throughput of 16 Mbps, 16.1. Earlier we had 7.2, now we are getting 16.1. Okay. You can even observe like all the remaining things are as it is, like we are not changing any properties. This congestion control algorithm we have changed and throughput increased from 7.2 to 16.1. Okay. We can also observe graph. Yeah, wait. Complete down. Little bit more. Yeah, fine. Try to click on black. Move it. The other side. You see here, initially we had a slow start phase. Currently we experienced some problem. Instead of coming back to 4500, we are going here. Okay, almost half of whatever the peak value we had. Okay, then that is going on like that. Then again here it is falling down means we are experiencing RTO timeout. Okay, let's take again. Okay, initially we have that falling to half. Then again, if you observe here, it is going from slow start. But here this was additive increase after condition additive increase. Then here it is increasing and going all the way here. Again RTO timeout. So it is falling down. So wherever we have straight line kind of thing, after falling, that is considered to be fast retransit. Okay. You can observe still if you have any. Again, here we wanted to go with that one, but again we experienced congestion, so we are coming back all the way to down here. Okay. And we can also observe this one, like when we go with this one also, congestion window size will be there. So you can see from this one also how it is changing. Okay, we are starting with 4380 and increasing. Okay. Anyway, for each packet you will have 2 to 3 entries. Okay, after 10,000 again it is falling down. And you see here we got some error. So we are falling down to 8760. Okay, successful, there is no change. Error, we are changing the value. And again, let's find another case of error. Just control it. Find next. Find next. See again, this is the first case. Then next. Okay. So here again we got error. So we need to check the packet number, packet ID. So we'll have to see like what is the packet ID for next packet ID, what is the congestion window size we are considering. Like that, if you observe, you will be able to notice these changes. Okay. So we can take some time and observe these changes. We can observe both in graph and also in Excel sheet. Wherever error is happening, we try to observe. Okay. So you can remove unnecessary columns so that you will have time value, packet ID, condition window, only those three.
As well as it is taking pain window.
No, you need to skip the packet ID. It will take one. I decide. Right. This is a word, but again 10,000 we are getting because this is for 10,000. Okay, eighth packet got problem. So we are retransmitting with different condition window, decreasing. Then here it is error 181. So next. हाँ We can also try graph between application generation time and corresponding condition window size. Like whatever the Wireshark graph we have seen, that graph we will be able to see. I think this starts. Anyway, if you just observe, like even you need to filter out these NA values. And if you see here, sometimes it is coming all the way till down. Sometimes you can see the graph is falling to some half portion. It's not completely coming down. Okay, that is taking a lot of time. What you can do is you can save that experiment and change protocol to Reno. That is Reno. And mostly we won't be able to observe much change when we consider Tahova and Reno with respect to graph. The reason is we are just adding extra 3 times MSS. So we won't be able to observe much change. Only with respect to throughput we will be able to observe significant difference. And with Reno, what is the throughput you are getting? 17.76. Okay. So as I told, we won't be having major difference when we consider Tahova and Reno, but little bit performance will be increased because here we had fast retransmit. Here we are considering, along with fast retransmit, we are also considering fast recovery. Okay. So these are not the only algorithms we have for congestion control. Even we have other algorithms like TCP Vegas, like that. Even if I've seen while selecting application in node properties, when you are selecting congestion control algorithm, we have also seen other options, right? Cubic is there. Okay. So in your theory, we have just TCP, old Tahova. So if you get a question in final exam, explain congestion control in TCP, then you will have to explain old Tahova. That is the case of slow start algorithm, additive increase and multiplicative decrease. Okay? Is it clear?
Yes, sir.
Okay. And you need to combine to that with like what is fast retransmission and what is RTO. We have one flow chart, right? Which talks about state transitions. That you will have to write. Okay. So you can note down the throughput values. Whatever the graph we have, that is for understanding how congestion window is changing. Major thing you need to take out this experiment is throughput. How throughput is changing when we are changing different congestion control algorithms. Completed? and the index. Go to fields. Yeah, the fields of